Welcome to the February 2020 edition of the AJP-Heart and Circulatory Physiology video table of contents, or From the Editor's Desk. The papers published this month represent some of the best basic cardiovascular science in the current literature. There's something here for everyone. So here's a sample of what's inside. In one of our premier Guidelines in Cardiovascular Physiology papers, Limburg et al. Discussed the do's and don'ts of using duplex Doppler ultrasound to assess blood flow under a variety of experimental conditions in order to study skeletal muscle resistance vessel function. This paper provides general as well as specific recommendations regarding the conduct of human studies involving Doppler ultrasound-based measures of resistance vessel function in skeletal muscle. In particular, the authors address topics related to experimental design, data collection, and signal processing, as well as review common procedures used to assess resistance vessel function, including post-occlusive reactive hyperemia, passive limb movement, acute single limb exercise, and pharmacological interventions. Chen and co-workers sought to explore the specific physical interactions between the carboxy termini of cardiac KCNQ1 and KCNE1 subunits that confer control of the alpha and beta subunits. Hydrogen deuterium exchange coupled to mass spectrometry narrowed down the region of interaction to KCNQ1 residues 352 to 374 and KCNE1 residues 70 to 81, and provided evidence of secondary structure within these segments. Key mutations of residues in these regions tended to shift voltage dependence of activation towards more depolarizing voltages. These results suggest that the proximal carboxy terminal regions of KCNQ1 and KCNE1 participate in a physical and functional interaction during channel opening that is sensitive to perturbations and may explain the clustering of long QT mutations in this region. Nakamura et al. Show that ADAM12 knockout mice exhibit significantly more advanced cardiac hypertrophy and higher mortality rates than wild-type mice 4 weeks after TAC surgery. ADAM12 deficiency resulted in significantly more expanded cardiac fibrosis accompanied by increased collagen-related gene expression in failing hearts. The loss of ADAM12 increases the abundance of the integrin beta-1 subunit and transforming growth factor beta receptor subtypes 1 and 3, and this was followed by the phosphorylation of focal adhesion kinase AKT, mammalian target of rapamycin, ERK, and SMAD2/3 in the heart, which resulted in cardiac dysfunction. Mullins and Bondarenko describe a mathematical model for beta-1 adrenergic regulation of mouse ventricular myocyte contraction. The model was able to simulate major experimental protocols for measurement of steady-state force-calcium relationships, cross-bridge release rate, and force development rate, force-velocity relationships, and force redevelopment rate. It also reproduced frequency and isoproterenol dependencies for calcium transients, total contraction force, and sarcomere shortening. The mathematical model suggested the mechanisms of increased contraction force and myocyte shortening upon stimulation of beta-1 adrenergic receptors is due to phosphorylation of troponin 1 and myosin-binding protein C, and increased calcium transient resulting from activation of the beta-1 adrenergic signaling system. A rapid report, Siva et al. Examined the effect of NOS inhibitors on mitochondrial respiration and protein S-nitrosylation. NOS inhibitors decreased the state 3U respiration in cardiac mitochondria, and both state 3 and state 3U respiration in brain mitochondria. In contrast, an eNOS inhibitor had no effect on the respiration in the mitochondria from both heart and brain. Interestingly, NOS inhibitors reduce the levels of protein S-nitrosylation only in brain mitochondria, but nNOS and eNOS immunoreactivity was observed in the cardiac and brain mitochondrial lysates. Thus, the effects of NOS inhibitors on S-nitrosylation of mitochondrial proteins and mitochondrial respiration confirm the existence of functionally active NOS isoforms in the mitochondria. Thank you for watching this month. We appreciate your support of the journal and hope we're doing our job to keep the best quality papers as high as possible. We will see you next month, and please don't forget to send us your best work now.